So today we're here to talk about harmonics in electric motors. As some of you might know, HBK is a provider of test and measurement equipment. We make sensors, data acquisition, and software. I bring this up partially because one of our legacy brands, Brule and Care, used to have some really great training material on things like FFT and frequency analysis. So I've stolen a bunch of that for today, and I hope this is of interest. All right, so we're going to start out really basic. I promise we'll get to kind of the meat of it in a moment. But for everybody who might be relatively new to frequency analysis, when we're measuring things, we kind of think and live in the time domain. So if we have a train timetable, the train comes at 6:10, 6:30, 6:50, so on and so forth. But when we start thinking in the frequency domain, we want to bin all of these things together. So we start thinking the train comes 3 times per hour. Rather than the train, it comes at these specific times, it's the train comes at 3 times per hour. So that's when we talk about time domain, it's, here are these discrete events. When we talk about the frequency domain, it's how frequently these events happen, which when we look at electric motors and inverters, because we're operating in the rotational basis, we have a lot of things happening at a given frequency. We have a lot of things happening periodically. And just to kind of further put some meat behind that, we have the physical world where we might have something like gears or a clock, and these are rotating elements. And these rotating elements, have kind of what we experience daily in sounds or vibrations. If you've ever had like an annoying sound coming from your refrigerator, that's very much something that's happening in time. So we have this time domain, maybe this little sound signal coming. But if we translate to that frequency domain, we see that we have a numeric description of how frequently we're getting, one of these peaks. So how frequently we're getting each peak. So these individual effects in the time domain are all mixed together. While in the frequency domain, we can actually make sense of it. Event A is happening this frequently with this much amplitude. And we can start to understand things like the noise is coming from our refrigerator, or if we're moving into electric motors, how the excitation of the motor takes place. So again, frequency analysis is taking time domain information, binning it into how frequently are these events happening. And this allows us to separate events and identify, sound A is coming from part A, sound B is coming from part B, so on and so forth. We can identify where problems are or where solutions might be. So as many of you might know, electric motors have excitation that's sinusoidal. And I think it's really important to stress that we almost never work in pure sine waves. I'll probably say that a dozen times today. What we work in is a conglomeration of different waves at different phases and different amplitudes. And we push all of these waves together and we get a complex waveform out. And this is a lot closer to the reality we deal with motor excitation. But it's also important because we can take this motor excitation, and this is a very ugly motor wave, I know. But this is coming from a sound and vibration presentation. Fascinating how similar the two are. We can take this kind of complex wave and we can break it into this, I've got this element with this amplitude and this frequency, this element with this amplitude, this frequency, and this phase. And we can break it down into its individual waveforms, which I think is really interesting and an exciting way to analyze these things. So getting a little closer to the actual motors and what the harmonics we're talking about are. So if we take an imperfect sine wave, so we have this square wave with this kind of wavy top and wavy bottom, an approximate square wave. Well, we can break that down into its different frequency components. We can break it down into the fundamental, that's kind of that main carrier wave, and then its subsequent harmonics, which, struggling to move my, and we can break it down into, we see a third harmonic element, we see a fifth harmonic element, we see a seventh. So we can take the square wave and break it down to kind of this infinite series of sine waves with different frequencies and amplitudes. And again, when we're getting into the harmonic analysis, that's exactly what we're doing. We're taking these kind of pseudo square waves or not perfect sine waves and breaking them up into their individual elements that are a pure sine wave with a frequency and an amplitude. So this is pretty exciting stuff because this gives us tools to do a lot of analysis, and whether these harmonics, these higher level frequencies are causing problems, we can start to mitigate that. Or, as we'll talk about a little bit, we can use some of these things to our advantage. So the harmonics are seen by these AC signals, and they have frequencies and amplitudes. So let's look at the motors a little more closely and look at the harmonics in our electric machines. So as, again, many of you probably know, we have sine waves or representations of sine waves or square waves that we excite our machines with. And we're going to see these as symmetrical square waves, symmetrical trapezoids, symmetrical sine waves. And the symmetry is really important because it eliminates the second order harmonics. Just by giving these things positive and negative parity, we can eliminate a lot of our second order harmonics. So this is pretty cool because if we're looking at this from problem solving, we don't have to worry about even things in our motors. We do, but not nearly as much. This also gives us the power to eliminate those 2N harmonics with trapezoids and square waves. So in my graph over here, my picture over here, I have, my symmetrical sine wave, my symmetrical square wave, my symmetrical trapezoid. And then I have these non-symmetric, and we're not nearly as frequently going to see these types of excitation. Just because they don't have that parity, they're going to throw off those second order harmonics. So in motors, this is why we're talking about, typically sine waves, but mostly waves with symmetry. All right, why 3 phases? Well, interestingly enough, if you run through the math, and I'm going to start with my chart over here on the right. If we take a motor winding and we have the A phase is wound at 0 degrees, the B phase is wound at 120 degrees, and the C phase is wound at 240 degrees, and we run sine waves through each of these. If we look at their third harmonic, if we remember back to what I just mentioned, the third harmonic is going to be 3 times the fundamental frequency. Well, 3 times 0 is 0. 3 times 120 is 360, and if we go into kind of our rotational, we remember our high school trigonometry, 360 is equal to 0. And for C, 3 times 240, 720 equals 0. The third harmonics in a 3-phase system cancel each other out. And that's pretty exciting, because again, we've eliminated the second order harmonics by having symmetry, and the third order harmonics are going to cancel out in the neutral, and they're going to eliminate our 3N harmonics. Now anybody who's operated in practice knows that very rarely do we actually have a balanced system, but this is a big part of the reason why we use 3-phase. Unbalanced loads have that third 3N harmonic in the neutral. But again, this gives us a troubleshooting tool. If we start seeing third harmonic, we know that we have an imbalance. And this also applies for anything that comes in increments of 3. So 3, 6, 9. We're seeing a lot of the German auto manufacturers go to higher phase count machines. They still get the benefit of this 3N parity. So we've eliminated the even harmonics. We've eliminated the tripline harmonics. But I haven't actually gotten to why we care about harmonics. And we'll get into more. But we have to start somewhere. So a couple of the reasons are we have losses that are associated with harmonics. We have reactive power that's associated with harmonics. We have positive and negative torque. And if we look at our fundamental, and I go back to this chart, our fundamental is 0, 120, 240. Again, that's the physical distribution of the windings, and therefore the distribution of the excitation. Now, if this is going in the positive direction, we're going A, B, C. A phase passes torque to B, passes torque to C. So our excitation, let's call it the positive direction. Third harmonic cancels out. We got no rotation. So the first one of interest, because we've eliminated our second order harmonics, is our fifth. And again, we go through our math, and now we get A, 5 times 0, 0. Fifth harmonic times 120 is negative 120. Fifth times 240 is negative 240. This guy rotates backwards. The fifth harmonic creates negative torque. It creates a torque that's going CBA. So if my rotation is in the positive direction, my fifth harmonic is causing torque in the negative direction. And it's the first one that we see. It's the biggest one. So this can be quite problematic. This can create noise, vibration, losses, torque ripple, all kinds of nasty stuff. So we want to start to understand things like our fifth harmonic. So again, we can mitigate them or maybe use them to our advantage. Seventh harmonic now goes in the positive direction. In theory, you could run the machine off the seventh harmonic because it's got positive phase direction. So again, if we think about it, if we understand our seventh harmonic, maybe we want to eliminate it. Maybe we want it to boost torque. Good question. Maybe we want to play with that in the fifth harmonic to eliminate, maybe some sixth order vibrations. It's interesting stuff that we can start to play with if we understand it. And then we get to our ninth, and naturally our ninth is eliminated because of the trip line. So we care because some of these can cause problems. If the third is there, that can cause a problem. If the ninth is there, that can cause a problem because something's out of balance. If the fifth is there, we might need to reduce it because the fifth is causing some negative torque or vibration or torque ripple. So, this is why we care, because we want to mitigate or we want to use things to our advantage. All right, so what are the causes of these, different frequencies in our motor excitation and therefore in our rotation? Well, here is, and again, many of you might be familiar with this. This is a PWM signal from an inverter. So my voltages are in blue and my current's in red. And, we have these discrete switches turning on and off. And if we look at my current waveform, we get this sawtooth pattern that's following those switches. We're charging up the inductor in the motor, we're discharging, charging, discharging. And we get this kind of fundamental sine wave, but we get this sawtooth feature. So the machine excitation is really important. What that voltage source is, whether it's an inverter, whether it's the grid, if it has, distortions in it, this is going to cause some harmonic content. So if we have things in our system that are causing a non-sinusoidal excitation, that's going to create harmonics. And inverters, if we remember back to that square wave we showed, that's an infinite series of sine waves. We have a lot of square waves here. We're injecting a lot of square waves into that current, into that voltage. So the inverter switching absolutely can cause harmonics. Those are going to be higher order at the switching frequency. I'm not going to talk about that a ton, but it's there. The machine control. These inverters, we have a lot of flexibility. We can throw trapezoids, we can throw square waves, we can throw heart-shaped waves. But all of these, again, have that harmonic content. So the excitation shape and some intentionally caused harmonics are going to result in that frequency domain information. And then, the excitation, even if it's a pure sine wave, could have interaction with the rotor, the magnets on the rotor, to, again, create harmonics in the profile. So we need to consider that inverter, that motor control, that machine excitation are going to cause harmonics, again, good or bad. A lot of people always, probably get this question, are harmonics good or bad? It depends, because there's some good ones, some bad ones. The motor construction, and this is almost more specific to permanent magnet motors, is very important for the harmonic profile. So I've got a lot of pictures here, so I'm going to talk through it. But basically what we have, we're going to start with picture D and work backwards. We have a rotor with a magnet on it. These little gray guys are our magnets. We see the magnets over here. Well, this magnet shape, and that could be the magnetic strength shape or the physical shape, that magnetic shape is going to create a back EMF when it's rotated by windings. This back EMF is going to have a profile. So the shape of the magnets is going to create some natural harmonic content. The placement of the magnets, the skew of the magnets, and then the interaction with the winding profile. So, the magnet shape, the magnet slot combination can create harmonics in our back EMF, in the voltage generated. Well, our back EMF is constantly interacting with our stator excitation. So if we look at, and this is voltage for different shapes of magnets. This is the voltage generated. So, we have kind of that perfect sine wave. We have this like more heart-shaped wave, and then we have a kind of a fatter heart-shaped wave. These are just different profiles of the same magnet. And if we look to the frequency domain, so this is the angle domain. This is if I just rotate it. This is the voltage generated. If we look at the angle domain, we can see that all these different shapes have, the pure sine wave doesn't have much third harmonic, but that fat sine wave definitely does. So the different shapes create different harmonic profiles. That back EMF is interacting with that stator excitation. That can create harmonics in our current, can create, again, torque, noise, vibration, subsequent from those harmonics. So we need to consider that our rotor shape, our magnetic shape, and our stator excitation, our windings, and our control all interact with each other. And that can cause that frequency content. All right, so what are some useful harmonics? Well, this is going to come down to a lot of inverter control because, a lot of times harmonics are creating losses where we don't want them, but we can do some clever things to control machines with them. So just remember that a lot of these control techniques, a lot of these things I'm going to talk about do come at the expense of efficiency and losses. So there's only so many ways to fool Mother Nature. We have all these trade-offs. So we often introduce harmonics to achieve a goal. By introducing things like the third harmonic, you can minimize neutral currents. If we look at a PWM inverter, we can't offer a pure sine wave. So we have to use what we have. Well, we can do things like if I have a fundamental that I desire in my red wave, I can use something like my third harmonic in my green wave, add those together, have my inverter output this blue wave, which is fundamental plus third harmonic, and we can increase the output voltage level. We can get more power out of a given inverter motor combination. So we can directly, take something like our third harmonic, inject it in, and get this really increased voltage, increased power out of our machine. The cost might be efficiency, but we can get a higher power with equipment we have today. Like we've already bought it, we've got it off the shelf. We can get a higher voltage output. So we can use clever tricks to increase power output. We also use it to reduce harmonics. If you have this blue waveform, we'll just inject the negative sequence of the green waveform, and you can maybe undo some of that. So you can start to eliminate, kind of think of it as like active noise cancellation. So the way we do this is we command a current with a different shape from our inverter, and we add these signals together, and we get more voltage output. So this is a good use. We can get more power. You can also use clever things with harmonics for predicting where the rotor is. So you can do self-sensing with harmonics. You can inject a high frequency signal. And again, in my graph on the right, we have the amplitude of current and the frequency. Or I guess this is d-axis voltage. So we have the amplitude of the d-axis voltage and then the frequency. And we can see that, we inject an 850 hertz signal. And that gives us the ability to sense where the rotor is. And this basically uses the machine saliency. We pulse a signal at the rotor. We read back what it's telling us. And this gives us, by injecting a high frequency or a harmonic injection, we can understand where that rotor is. And this gives us a lot of tools for controlling and for predicting what the machine is going to do. Now, this might introduce some torque ripple. It might introduce some loss. But if we take a comparison of, an angle encoder and the predicted angle from the harmonic injection, that tracks really nicely. So we can do clever things with understanding where the machine is, controlling the machine. So this is pretty cool. We can use things like high frequencies to predict where the machine is. Torque ripple suppression. We can inject harmonics at a certain area in the machine, in the synchronous or stationary reference frames, again, depending on motor type. But it's basically active noise cancellation for torque. So if we have a torque ripple, we can inject harmonics into the current to try to eliminate that. And here's an example from a paper General Motors recently published, where they're actually looking at the vibration content versus motor speed. And we can see that in this example, they have the same control technique running. And then for the baseline and the torque ripple compensation, they turn on their torque ripple compensation at about 2200 RPM. And we can see that vibration notably decrease just by injecting that harmonic. We can see that sound power level notably decrease just by injecting those harmonics and reducing the torque. So we can use clever tools like harmonic injection to create a better experience from the machine. But again, we need to be able to measure and control those, which I promise I'm getting to the measurement. So we can do torque ripple suppression with harmonic injections, with using our harmonics advantageously. Again, we're probably going to be at the cost of a little loss, but we have to look at what our end goal is. All right, so measuring harmonics. Now, again, I'm going to take you back to some basic electrical engineering or maybe one of your entry-level math classes. I am not going to dig through the details because honestly, I don't remember the math. But a lot of these techniques that we're going to use utilize the fast Fourier transform or the discrete Fourier transform. And all we need to remember is that the Fourier transform is a mathematical filter. We enter an equation into an algorithm, we use complex numbers, and we take our kind of abstract sine wave and we extract, and this did not turn out good on my slide, I apologize. We extract those different frequencies. So we can pull out, this is X frequency and Y amplitude, and then we can plot that out. So we can take our wave and we can understand what all those amplitudes and frequencies are. Now, when we talk about measurement, we need to remember that we need to have a sufficient sample rate, or a sufficient sample time and a sufficient sample rate. So because we're doing a frequency analysis and we're looking over a period of time for how many events are happening, we need to have enough time for those events to happen. And kind of the quick example is if we were to blast a sine wave. Well, if we have 4 rotations of that sine wave and we perform our FFT, so we have our little G of t goes into our FFT, comes out with a big G of t, we can see that we have a frequency at a given amplitude at a very specific frequency. Well, now, okay, we reduce that from maybe 4 sine waves to 3. We don't have as much information. The mathematical transform can't act as well, and now we see these kind of weird ripple guys centered around our main frequency. We don't have enough samples, we don't have enough time window, we don't have enough occurrences of the frequency to really say for sure it's this very specific frequency. And then we go down to 1 sine wave and we see that we barely know what the frequency is. So we need to remember, we need to have a big enough window to have several events happen because we're picking out that frequency. But we also need to sample at a rate high enough that we're not aliasing the signal, that we actually have all the frequencies of interest. Oh, wrong direction. So kind of getting into the more nitty gritty details. On the right-hand side, I have a current, microphone, and a torque. So the torque is in black. And if we take the frequency domain, we can see just kind of very traditional FFT of amplitude on the Y versus frequency on the X. And just a couple notes, again, from the measurement side. We need to measure the signal at a significant or a sufficient bandwidth. So, everybody always quotes the Nyquist frequency, which is 2 times the frequency of interest. But if we really look at the details of measurement, we need to look at the filters of our measurement system. We need to look at, what the sampling rate is. And we need to filter higher than the frequency of interest. So we need to make sure that our frequency of interest has sampling rate way sufficient and then filters above that frequency of interest, because we need to do things like anti-aliasing, because we need to do things like signal conditioning. So you need to really understand what the bandwidth of your amplifiers are. Just because your sample rate is super high does not mean you're going to catch the signals of interest. You could filter it away. So you need to check both your sample rate and your filters. We have a variety of different analysis types we can do. All of them do rely off of kind of the Fourier analysis, but we have the FFT, which is featured here. It's really quick and easy, but it might actually give us too much information typically. We could do a harmonic order analysis where we do it based off the speed of the machine. But in this case, we need to know about the fundamental frequency, and I'll touch on each of these a little bit more. And then we can do things like harmonic power analysis, where if we know the different harmonic orders and we can identify the harmonic phasing, we can start to understand what is the power from these different harmonics. How much energy am I losing because of these different harmonics? And this is where we get really into a deep understanding. if I'm doing a third order or a third harmonic injection, is that creating extra losses that mitigate its purpose? And all of these techniques can be executed on any signal: current, torque, acceleration, microphones, vibration. Order analysis is really key to things like um, vibration and noise. And I'm sure there's a lot of NVH engineers in here falling asleep with my kind of basic overview, but I think we'll forget the basics quite a bit. All right, here's my baby sales pitch. HVK does make equipment. I'm going to show some examples. We used our eDrive power analyzer where we measured voltages and currents at a sufficient bandwidth. We stored the data, we did some analysis, and we do have sensors that offer the high bandwidths as well. If you want to talk about that, please catch me offline. I don't want to belabor that. But in our software, we can do things like a simple FFT. I showed an example of this earlier, but it is a really powerful tool, and we do show this live in the software. So if you're measuring a voltage and a current, you can look at, all right, what is my fundamental? What are my harmonics in, 5th, 7th, 11th, 13th? And then what are my switching effects? And we can really see the full spectrum out to the bandwidth of the amplifier. So we can get a good understanding and kind of a gut feel on what's happening in the frequency domain. Start to line up things like torque. It's a quick snapshot. It's calculated over a window. But it's a good way to understand what you're doing. I personally don't get the most information out of this, more than just a quick health check on what's happening in the machine. Do I have noise? So it's a powerful tool, but I think there's things we can get more information out of. So I mentioned fundamental-based harmonics. This one I think is really powerful for doing analysis, and it's actually dictated by a lot of aerospace standards, where you want to identify what is the frequency of the sine wave. So we have a sine wave. In this instance, I have a current in red. And in our hardware, we actually track the frequency with some cool digital algorithms, and I get a square wave that's kind of my half cycle. So every half cycle, you want to do an analysis. So we take that frequency, and then we do our FFT and we do our harmonic analysis based every half cycle. This allows us to understand, what are my harmonics that are a function of that fundamental frequency. The FFT, I'm looking at everything. I'm looking at things that are not included in my fundamental. I'm looking at weird asynchronous events. Now on the fundamental basis, we're just looking at that third harmonic, that fifth harmonic, that seventh harmonic. So this is a really cool tool to really do an order analysis for those of you who are familiar with that. And our measurement system is kind of special that we can do this very quickly. Again, we can talk offline, but we're doing those calculations on this square wave basis. This is our frequency. And then we can take things like a number of sine waves, we can bunch them together, and we can give you a chart that is outputting what is my fundamental, my second, third, fourth, fifth, so on and so forth. Break it down to what is the amplitude of those orders of the fundamental, what are those harmonics? We can give you a percentage and what the frequency they're occurring at is. So this is a really cool way to kind of understand the spectrum of your signal and get it in a really nice bin graph where we eliminate all those non-order-based harmonics, where we eliminate all that other frequency content that's not from our sine wave. We're just looking at those harmonics of the fundamental. So this is a really powerful tool for starting to understand, what is my presence of third? What is my presence of fifth? What is my presence of seventh? And then make decisions if they're good, if they're bad, understand if you're implementing mitigation techniques, if it's being effective. And I think this is my last slide, but this is my favorite. One of the cool things we can do as well, we take that cycle-based information, we use that frequency, and then we can calculate what is the RMS of our fifth harmonic current. What is the RMS of our fifth harmonic voltage? And then even better, we can say, what's the phasing between these two? And if if anybody remembers their kind of power equations, we have VRMS times IRMS times the cosine of phase. Well, if I have VRMS of the fifth, I have IRMS of the fifth, and I have the phase of the fifth, I can calculate, fifth harmonic power. And again, we have a graph here where this is a screenshot from our software where we can see that fifth harmonic voltage creeps up per given operation. We can see that fifth harmonic phase changes as we creep up. We can see our fifth harmonic current creeps up during this given operation. We can see our phase stays pretty consistent. And then we can see that we have 10 watts of power or so that show up in our fifth harmonic for this given machine. And you can start to decide, is this injection causing a lot of loss? Is this unintentional harmonic causing a lot of loss? And we can do this for all of our harmonics. And I think this is really powerful for starting to understand where losses go in our machine. And this is something we can display live. This is something that you can do post-process, but with our system, we store the data and we give you an easy way of doing these calculations. I did have some references through here, some really interesting papers, including that old B&K training. But with that, I would like to thank you guys for your time. I hope this was useful, and please reach out if there's any questions.